Jnanam paramam dheyam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. As a part of our ongoing discussion on organometallic catalysis reaction, we have been looking at C1 chemistry, particularly that of carbon monoxide utilization chemistry from an industrial standpoint in the last two lecture. Now, what we had observed is that though olefin oxidation reactions are important and are being used in industrial scale. For example, the Walker oxidation of ethylene to acetaldehyde is being used in industry for more than a century now, or that of halcon arco oxidant epoxidation reaction, in which propylene is converted to propylene oxide in about 6 million tons a year annually. There is a need to develop this CO utilization chemistry, particularly this chemistry C1 chemistry, which is more popularly known as. Now, with respect to this, we have been talking about these two reactions, the water gas shift reaction and Fischer-Tropsch reaction, and what we have discussed is this water gas shift reaction is a reaction that affects the oxidation of CO to CO2, whereas Fischer-Tropsch reaction affects the reduction of CO to hydrocarbons. So, in a way, both of these reactions are important and are need of the day, as the concentration of CO continue to grow in the environment and has become a global nuisance and hazard, and there has to be a remedial steps required to cut down on CO emission. So, from this perspective, this water gas shift reaction becomes important. In our past discussion, we have also looked at the various methods which contribute to the CO gas, CO in synthesis gas, and they are generally from three sources, which are mainly controlled combustion of crude oil or reforming of natural gas or coal gasification reaction. The controlled oxidation of crude oil gives the synthesis gas, which is carbon monoxide and hydrogen, and coal gasification also is the reaction of carbon with water to give CO and H2, and of course the reforming of natural gas. Now, with this we have discussed these two formation of synthesis gas, and then we will talk about this equilibrium in water gas shift reaction in bit more detail. The equilibrium in water gas shift reaction is the reaction of water with carbon monoxide in presence of heterogeneous catalyst based on iron and copper that produces hydrogen and CO2. So, H2O plus CO catalyst iron copper, these are heterogeneous catalysts at temperature greater than 200 degrees centigrade, producing hydrogen plus CO2, delta H equals minus 42 kilojoule per mole. Now, the significance of this equilibrium lies in the fact that these are the depending on where the equilibrium lies, one can envision this reaction as carbon monoxide getting oxidized by stripping this oxygen from water, and in turn producing carbon dioxide and hydrogen. So, significance of this reaction lies in exploitation of the reducing power of CO to produce hydrogen from water under mild condition. The significance lies in being able to produce H2 from CO and H2O under mild condition. Highlighting the reducing power of CO, highlighting the reducing power of CO. The removal of this process also has a significance, because this allows removal of CO from the gas mixture of Haber-Bosch process, which is used for making ammonia by reaction of hydrogen and nitrogen. So, also lies the significance also lies in the removal from the mixture for Haber process. Hydrogen enrichment of the synthesis gas for Fischer-Tropsch reaction. Synthesis gas for Fischer-Tropsch synthesis. So, this reaction is kind of very important, because this exploits the reducing power of CO, produces hydrogen under mild conditions, and also removes CO from the gas mixture for the Haber-Bosch process, and also leads to hydrogen enrichment in the Fischer-Tropsch synthesis. So, this is really a important reaction that exploits the reducing power of CO, and itself CO gets oxidized to produce carbon dioxide, and water get reduced to hydrogen. So, this is an interesting reaction. Now, current the main challenges involves heterogeneous catalysis, which involve high temperature, is unfavorable for equilibrium for water gas shift reaction, and that sort of provides the impetus for carrying out the reaction under homogeneous conditions. So, current heterogeneous catalysts involve high temperature, which are unfavorable for the position of equilibrium. For the equilibrium, and this is the reason why homogeneous catalyst which can do this reaction under more milder conditions are required, and for which homogeneous catalysis under mild conditions are required. Now, in these homogeneous conditions for mild conditions required. Now, one would think that how would a homogeneous catalyst be able to carry out this reaction under mild condition, and the main rationale to that is that under homogeneous catalysis, the nucleophilic activation of CO may be performed by coordination of CO to the transition metal followed by addition of the nucleophile. So, this is an important strategy which sort of would be used for carrying out this oxidation of CO2 carbon dioxide. So, the strategy, the main objective, main target in this front is the nucleophilic activation of CO by coordination of CO to transition metal followed by addition of nucleophile to the carbon atom. And this is simply represented by the schematic representation, where metal plus carbon dioxide monoxide forms the activation through coordination to give MCO, and then the nucleophile acts on the carbon, which this step is called nucleophilic activation, to give MCO/NO. So, homogeneous catalysis thus provides a very systematic approach of activating this carbon monoxide molecule by coordination of the carbon monoxide to the metal center, followed by the nucleophilic attack occurring at the carbon. Now, activation of substrate by coordination to transition metal is not new in homogeneous catalysis, but on the other hand it is a very common step in homogeneous catalysis, and we have observed this in many catalytic reactions, particularly with respect to olefin activation reactions, where olefins get activated primarily by coordination to transition metal. So, similar strategy can be put in place for the CO activation followed by nucleophilic attack on the carbon of the activated CO, resulting in MCO nucleophile, and this is the strategy that is sought for achieving milder conditions using homogeneous catalysis for this water Graff shift reaction, in which CO can react with water to produce hydrogen and carbon dioxide. So, this this activation of CO by coordination can be so effective that even weak nucleophiles like water can undergo reaction. So, and this is explained by the reaction is explained in Haber's base reaction given by two catalytic cycles. Haber base reaction. It is given by two catalytic cycles where even water can be used, weak nucleophile can be used to attack the carbon monoxide coordinated metal oxide. So, the reaction starts with a metallate, for example, H Fe CO4 minus. First, obviously, is the reaction with CO giving Fe CO5 plus H minus. Now, this carbon monoxide gets coordinated to iron giving FeCO5 and the hydride leaves. This H minus then reacts with water to give dihydrogen H plus, and this water gets deprotonated by H minus to get OH minus. So, beautiful chemistry in the offing, and this OH minus then attacks this CO coordinated to transition metal. A wonderful example in which by using a metallate anion water is activated by deprotonation of water with the iron hydride generating H2 and OH minus. Now, this OH minus attacks the coordinated carbonyl to give FeCO4 and FeCO4 would then decarboxylate to give CO2 and along with the regeneration of FeHCO4 minus. So, wonderful chemistry in which this catalytic cycle is based on, and this adopts the principle that the CO gets activated by coordination to iron, and then the nucleophile, which is OH minus generated from this metallate anion consisting of a hydride. This metallate anion then attacks to convert into acid, and then subsequently the acid decarboxylates giving out carbon dioxide along with this generation of iron hydride tetracarbonyl anion. So, this is a wonderful example for this Haber base catalytic cycle. There is another similar Haber base catalytic cycle which has been proposed, and we are going to sort of look at this catalytic pathway as well. Haber base reaction. This reaction also starts with this iron hydride tetracarbonyl anion, the reaction of water giving OH minus. So, this OH minus, and then as a result H plus is generated. So, this water sort of gets deprotonated by this iron hydride tetracarbonyl anion, resulting in iron dihydrogen tetracarbonyl complex. So, this is an elegant chemistry in place, can be seen for both of the catalytic cycles. So, here what we see that this iron hydride tetracarbonyl anion deprotonating water to generate OH minus, along with formation of a dihydride iron tetracarbonyl compound, which even loses this dihydrogen molecule by reductive elimination to give iron tetracarbonyl, and that now reacts with carbon monoxide to form the Fe carbonyl coordinated FeCO5. So, once this FeCO5 so formed reacts with OH minus, which has been released in the first step, and this OH minus then attacks to the carbonyl moiety bound coordinated to iron, as was the suggested scheme of activation. So, OH minus then attacks one of the coordinate carbonyls to give FeCO4 OH, and then that similar to what we had discussed earlier, decarboxylates giving CO2 and HFeCO4 minus. So, what one sees that this is a wonderful chemistry in which the reaction of carbon monoxide with water leads to the formation of carbon dioxide and hydrogen, carbon dioxide and hydrogen as have been desired under mild condition using a homogeneous catalytic pathway. So, this is a wonderful demonstration of the fact that how people on going from heterogeneous catalytic pathway, which also used this conversion of H2O plus CO giving H2 plus CO2, but it required temperature at over 200 degrees centigrade, very harsh condition. Such a conditions be reduced by proper choice of catalyst, homogeneous catalyst, in which in this case is hydride iron tetracarbonyl minus, and then it just simply converts this water to a hydroxide nucleophile along with regeneration of H2 and formation of carbon dioxide in a catalytic fashion, and bring down the difficulty in performing this reaction. So, this is two wonderful examples of homogeneous catalysis that have been used to carry out water gas shift reaction. So, metal carbonyls in general catalyze homogeneous reactions in basic medium. So, one can see the reason for the medium to be basic, because one has to deprotonate this water and generate this OH nucleophile. So, catalytic water gas shift reaction are performed by by metal carbonyls in basic medium. There are apart from iron species, the rhodium species of the type rhodium iodo CO carbonyls also able to catalyze water gas shift reaction, and the equation is given as below. The rhodium I2 CO whole 2 minus, and this is plus 1 oxygen state, and rhodium 3 I5 CO 2 minus catalyze water gas shift reaction which is present under conditions of R rhodium dicarbonyl chloride dimer, HO acetic acid, HCl and Ki. The reaction is given as follows: rhodium 3 plus CO plus H2O giving rhodium 1 plus CO2 plus 2 H plus, and rhodium 1 plus 2 H plus giving rhodium 3 plus H2. So, the overall net reaction can be written as CO plus H2O giving CO2 plus H2. So, with this I would like to conclude this today's discussion on water gas shift reaction, and what we have discussed in today's reaction is that this water gas shift reaction, which is very important particularly with respect to utilization of carbon monoxide, and this can be achieved by reaction of carbon monoxide with water, and this produces carbon dioxide and hydrogen, and this reaction is affected by transition metals with catalysts like iron, and these reactions are carried out under heterogeneous conditions that they require very high temperature of above 200 degree centigrade, which sort of shifts the equilibria of water gas shift reaction in an unfavorable way, and because of which more milder approach consisting of homogeneous catalysis are required. And from the strategy that has been used for carrying out this reaction under homogeneous catalytic condition is the utilization of the fact that this carbon monoxide can be activated by coordination to transition metal followed by nucleophilic attack at the carbon on the transition metal. Now, coordination substrate activation by coordination to transition metal is not a new concept in homogeneous catalysis, and most of the catalytic reactions do proceed by getting activated through coordination to transition metal. Indeed, the metal carbonyls under basic conditions like iron, carbonyl, tetracarbonyl hydride anion in presence of water do carry out this water gas shift reaction under catalytic fashion, in which it uses water and carbon monoxide and produces carbon dioxide and hydrogen. Not only and there has been 2 catalytic cycles that have been proposed for this transformation. Iron apart, rhodium carbonyls also catalyze this water gas shift reaction and in a 2-step process. The first step involves the reaction of rhodium 3 with carbon monoxide and water giving rhodium 1 and carbon dioxide and twice H plus, and the subsequent step involved rhodium 1 with H plus giving rhodium 3 and H 2. So, overall this rhodium 1 and rhodium 1 cancels out and rhodium 3 and rhodium 3 cancels out. The net reaction which comes out of it is that CO plus H 2 giving CO 2 plus H 2. So, this is exactly what is expected of the product for water gas shift reaction, and that can be achieved in a homogeneous catalytic fashion under mild condition. So, with this I would like to conclude today's discussion on water gas shift reaction and then take up this topic in bit more detail in the subsequent lecture, in where we would also look at the other aspect of the C1 chemistry, which involves reduction of carbon monoxide to hydrocarbons as a part of Fischer-Tropsch synthesis. So, I once again thank you for patiently listening to me in this lecture, and I look forward to take up this Fischer-Tropsch synthesis in bit more detail and also continue on the water gas shift reaction. Some aspect of it still remains to be discussed in the next lecture. Till then, goodbye and thank you.